Hey there, and welcome. Have you ever stared at a complex circuit diagram and just felt that calculus headache coming on? Well, today we're going to talk about an incredible tool that lets you swap out all those messy differential equations for some nice, clean, simple algebra. All right, let's jump right in.
So here's our game plan. First, we'll talk about why we even have this calculus headache to begin with. Then we'll escape to a much simpler world called the S domain. We'll see how to convert our circuit parts, solve problems with basic algebra, and then figure out what those answers are actually telling us. And finally, we'll bring it all home with a really important real-world example.
Okay, so let's set the stage. Why do we even need something like the Laplace transform? Well, it all comes down to the fundamental way circuits work.
And that's really the million-dollar question, isn't it? I mean, when we're trying to figure out how voltages and currents are changing from one moment to the next, especially when you've got capacitors and inductors in the mix, the math can get out of hand fast. And there it is. That's the culprit. You see, the behavior of these components isn't just simple multiplication. It's described by the language of calculus. And solving these differential equations, especially when you have to keep track of any initial energy stored in the circuit, well, it can be a real slog.
But what if we could just sidestep all of that nasty calculus? This is where our story takes a really cool turn into a new and much friendlier place, the S domain.
This right here is the magic trick. This is the big trade-off. The Laplace transform lets us change those difficult differential equations from the time domain into straightforward algebraic equations in the S domain. We're trading hard calculus for easy algebra, and believe me, that is a trade you want to make every single time.
So you can think of the Laplace transform as our bridge, our portal between these two worlds. And here's the absolute best part. It automatically deals with the initial conditions for us. You know, that starting voltage on a capacitor or the current in an inductor. It just gets baked right into the new equations. It's a huge time saver.
Okay, enough theory. Let's get practical. To start working in this new S domain, we've got to know what our basic building blocks, resistors, inductors, and capacitors actually look like over there. Let's see how they change.
Let's start with the easy one. A resistor is still a resistor. No matter where you are, time domain or S domain, good old Ohm's law works just fine. Voltage equals resistance times current. Nice and simple. All right, now for the inductor. This is where things get really cool. Inductors store energy, right? So it might have some initial current already flowing through it when we start looking at the circuit. We'll call that I0.
And check this out. This is how we handle that stored energy. In the S domain, the inductor becomes something called an impedance, which is S times L. You can just think of it as a fancy kind of resistance. But that initial current, it becomes its own little source in our model. We can show it as either a voltage source or a current source. The initial condition is no longer something we have to track separately. It's part of the circuit itself.
Okay, next up is the capacitor. And it's a similar story. A capacitor stores energy as an electric field, which means it might have an initial voltage across it, which we'll call V0.
And just like the inductor, that initial energy gets turned into a source in the S domain. The capacitor's impedance is 1 over SC. You'll also see admittance there, which is just the inverse of impedance, basically how easily current can flow. So that initial voltage becomes either a voltage source in series or a current source in parallel. It's just a really elegant way to handle things.
So we've done it. We've translated all our parts. Our entire circuit now lives in the S domain. And all that calculus has just vanished. Now we get to solve it using the algebra skills we already have.
And the key idea for doing this is the transfer function, or H of S. All it is a ratio. The circuit's output divided by its input, all in the S domain. You can almost think of it as the circuit's unique fingerprint. It describes how that circuit will respond to any signal you give it, assuming you start from zero energy. This really boils the whole process down to 3 straightforward steps. First, you redraw your circuit using those S domain models we just talked about. Second, you use your normal circuit tools, like Kirchhoff's laws, to write and solve the equations, but now it's all just algebra. And third, you use the inverse Laplace transform to translate your answer back from the S domain into the time domain, which gives you the real-world answer you were looking for.
Now, getting an answer is one thing, but knowing what it means is where the real insight is. And the beauty of the S domain is that it neatly splits the circuit's behavior into 2 different parts.
A circuit's total response is really 2 stories told at once. You have the transient response. That's the circuit's own natural reaction. Think of it like ringing a bell. That initial ding is the transient part. It's determined by the circuit itself, and it eventually fades away. Then you have the steady-state response. This is how the circuit is forced to behave by the input signal you're feeding it. This part sticks around for as long as you keep that signal on.
Okay, this is all fascinating stuff, but let's connect it to a real-world problem where this isn't just a neat trick, it's absolutely essential for safety. So picture this, you switch off a big machine. That sudden change can cause a huge, temporary voltage spike. That's a transient surge. And the big question for any engineer is, will that spike, on top of the normal voltage, be enough to fry other components in the system? The Laplace transform is the perfect tool for this, because it gives us the complete picture. It adds that transient surge and the steady-state voltage together so we can see the absolute peak voltage and make sure our design is safe.
And this quote just nails it. This isn't just about finding some abstract answer. It's about finding the full answer to make sure our electronics are robust enough to handle the real world. It's about designing things that don't break.
And that leaves us with a pretty cool question to think about. We just saw how jumping from the time domain to the S-domain turned a really tough calculus problem into simple algebra. It really makes you wonder, what other complicated problems out there in science and engineering are just waiting for the right change in perspective to suddenly become easy?